Dear students, this is Roseline, Assistant Professor, PG Department of Computer Applications, St. Joseph's College of Arts and Science, Cuddalore. Now, I would like to discuss about memory management. The memory management, we are going to see about memory hierarchy, main memory, cache memory, and virtual memory. First, we'll see about memory hierarchy. Memory hierarchy is to obtain the highest possible access speed while minimizing the total cost of the memory system. The memory hierarchy consists of CPU, cache memory, main memory, I/O processor, and auxiliary memory. In this hierarchy, if the CPU wants to access any information, first it will search it in the cache memory. If it is available, it will be transferred to the CPU. If it is not present, it will search it in the main memory. From main memory, the data will be directly transferred to the CPU. Suppose the information is not present in the main memory, it will be searched in the auxiliary memory, that is from magnetic tape or from the magnetic disk. From this auxiliary memory, the actual data will be transferred to the main memory through the I/O processor. Again, the copy will be placed in the cache memory as well as in the CPU. Hence, in auxiliary memory, the data will be transferred from magnetic tape or from the magnetic disk. Then finally, the data will be transferred to the main memory and then to the cache memory. Then the data will be actually transferred to the register which is available in the CPU. This is the actual memory hierarchy. Now, we'll see about the main memory. The main memory, we are going to have two chips. One is RAM and ROM chip. First, we'll see about the RAM chip. This is the actual diagram of RAM, which is having various control signals. Chip select 1, chip select 2, read, write, and it is having 7-bit address and also it is having 8-bit data bus. The size of the RAM is 128x8. This is the function table in which CS1, CS2, read, write, memory function and state of the data bus are represented. When CS1 and CS2 bar is equal to 00, 01, 11, 10, the memory function is inhibit and the state of the data bus is high impedance state. When CS1 is equal to 1, CS2 bar is equal to 0 and write is 1, it will perform the write operation, that is input data to RAM. When CS1 is 1 and CS2 bar is equal to 0 and read operation is 1, it will perform the read operation, that is output data from RAM. This is the typical ROM chip which is having chip select 1, chip select 2 and 9-bit address, and it is going to have unidirectional 8-bit data bus. The size of ROM is 512x8. This is the memory address map table which is going to connect 4 RAMs and 1 RAM to the CPU. The memory connection to the CPU is shown in this particular diagram. RAM and ROM chips are connected to a CPU through the data and address buses. The lower lines in the address bus select the byte within the chips and other lines in the address bus select a particular chip through its chip select inputs. This particular table shows the memory address map. It is going to represent the address of 4 RAMs and also it is going to specify the address of ROM. This is the connection between the CPU and memory. The CPU is going to have 16-bit address in which 1 to 7 address bits are used to identify the RAM and 8 and 7 address bits are used to identify the ROM. In addition to that, the CPU is having read and write signal and also it is having data bus through which the CPU can communicate with the RAM as well as with the ROM. Now we'll see about cache memory. First, we'll see about locality of reference. The references to memory at any given time interval tend to be confined within a localized area is called as locality of reference. The cache memory is directly communicated with the CPU and CPU can communicate with the main memory, but the CPU will search the information in the cache memory, not in the main memory, because the size of the cache memory is smaller than the size of the main memory. Hence, the access speed will be increased in this method. The cache memory, we are having 3 different techniques. One is associative mapping, direct mapping and set associative mapping. First, we'll see about associative mapping. In associative mapping, the entire cache is divided into two parts. One is address part and data part. The CPU is going to provide the 15-bit address which is stored in the argument register. In the argument register, address bit is compared with the address part of the cache memory. If the address is same, then the relevant data will be transferred to the CPU. Next, we'll see direct mapping. In direct mapping, the CPU is going to provide the address bit which is in the argument register. In this particular address is divided into two parts. One is stack part and the index part. The index part is compared with the cache memory, but the tag will be stored within the cache memory. Hence, the entire cache memory is divided into two parts. One is tag and index. The address register is going to specify the tag part as well as the index part, but the index part is compared with the address in the cache memory. If the index part is same, then it will compare the tag part. If the tag is also same, then the data will be transferred to the CPU. This is another technique in direct mapping. In this method, the entire address is divided into three parts, that is tag and index. Then, index is again divided into two parts, one is block and word. Hence, the cache memory is going to have 64 blocks, that is from 0 to 63. Each block it is going to accommodate 8 words. If the CPU wants to access any information, first it will check the block. If the block number is same, then it is going to check the word. If the word is same, then the relevant data will be transferred from the cache memory to the CPU. The main advantage is, if it wants to access any new data, the entire block will be inserted into the cache, as well as if it would like to transfer any data, the entire block will be removed from the cache. Hence, in this method, the hit ratio will be increased. We'll see the set associative mapping. In this method, the entire cache is divided into 4 parts, that is tag, data, tag and data. That is, for each and every address, it is going to store 2 datas. So, in this method, the hit ratio will be increased than the remaining methods. And also, this method is going to accommodate more number of data. The particular address is matched with the index part. If the index part is same, then it will match the tag part. If it is same, the relevant data will be transferred to the CPU. In cache, there are 2 techniques. One is write through cache, another one is write back cache. First, we'll see about write through cache. If there is a hit, both cache and memory is written in parallel. If there is a miss, memory is written. In write back cache, if there is a hit, only cache is written. If there is a miss, missing block is brought to cache and write into the cache. We'll see the virtual memory. The virtual memory it is going to give you the illusion that it is having a very large memory, even though the computer actually has a relatively small memory. The virtual memory is considered as address space and main memory is considered as memory space. The address which is used in virtual memory is called as virtual address or logical address. The address which is used in main memory is called as physical address. We'll see the address mapping, how the virtual address is converted as the actual physical address is represented in this table. The CPU is going to provide the actual virtual address which is stored in the virtual address register. Then particular address register is transferred to the memory mapping table, which is going to reduce the virtual address into a physical address. That is transferred to the memory table buffer register. Then it is transferred to the main memory address register. Then it will find out the actual address in the main memory. Then the data will be transferred to the main memory buffer register. This particular memory mapping table is used to reduce the physical address into a It is used to reduce the virtual address into a physical address. This is the address mapping. In this method, address space is divided into equal part and memory space is divided into equal part. The address space is called as pages. Memory space is divided into various parts. They are called blocks. The page size and block size are going to be the same. Now we'll see the organization of memory mapping table in a page system. The CPU is going to provide the virtual address, which is of 13-bit. The first 3 bits are page number, remaining 10 bits are line number. This particular page number is compared with the table address in the memory map table. Say for example, if the page number is 101, it will be matched with the table address. Then the relevant block number 1001 with the presence bit 1 is transferred here. Then hence, the page number is reduced as the block number, which is transferred to the main memory address register. Hence, the page number 101 is reduced as block number 01, which is available in the main memory, that is block 1. Then, the line number is going to be the same for both page as well as the block. Hence, the relevant line number is searched in the block 1, that will be transferred to the memory buffer register. This method or this table is used to reduce the page number as a block number. This is another technique, that is associative memory page table in virtual memory. The actual physical address is stored in the argument register, which consists of page number and line number. This particular technique is going to maintain one table, that is associative memory. This table is divided into 2 parts. One is page number and block number. The argument register page number is compared with the page number in the associative memory, provided the key register value should be 1. If it is same, then the relevant block number is transferred. This method is not having any memory mapping table. Instead, this is maintained using associative memory technique. Now we'll see page fault. If the page which is searched by the CPU is not present in the main memory, then it is called as page fault. If the memory is full, it is not possible to accommodate any new page, then it will use some standard algorithms. The replacement algorithms are FIFO and LRU. FIFO algorithm select the page that has been in memory the longest time using a queue every time a page is loaded and its identification is inserted in the queue. The next technique is LRU. Replaces the page which has not been used for the longest period of time. Thank you.